Hallo, ich bin Eberhard Wolf. Freitags mache ich oder Lisa Moritz einen Livestream zum Thema Softwarearchitektur, oft zusammen mit Gästen.
Dieser Podcast ist das Audio des Streams. Weitere Folgen, Sketchnotes und vieles mehr findet ihr unter software-architektur.tv.
Softwarearchitektur im Stream.
So, welcome everybody to another episode of Software Architecture on Stream. This time around with Hillel. Hi, Hillel. Great to have you
Hello.
on the show again.
Thank you for having me.
Do you want to say a few words about yourself?
Sure. So my name is Hillel, as mentioned. I work in a few spaces in software. I'm mostly known for doing work in this space called formal methods, which is how you prove designs of software mathematically correct. But I also do a large amount of history and journalism in software. I'm working on this piece right now about the history of regular expressions, and I recently published a piece interviewing people about why graph types aren't present in programming languages. And I believe this stream is going to be about one of my earlier projects, which is, are software engineers really engineers?
Exactly. So this is what we are going to talk about. First off, so why does that question matter to you? So why is it important to you? Why did you do research on it?
Okay, so as mentioned, I work full-time in a space called formal methods, which is, again, proving software correct. And that, to a lot of people, feels like a very engineering topic. You're sort of coming up with these like really rigorous blueprints and verifying them and showing that your software doesn't have bugs. And everybody in this space, like me, believes that like software isn't really a branch of engineering, that we don't really deserve the name. But I've also read a bunch of people online who sort of say the opposite, that like software isn't a branch of engineering because engineers could never do what we do. They would never have to deal with, in the words of, I believe, Jeff Atwood, the inventor of Stack Overflow, they would never have to build a bridge on Jupiter with the laws of physics constantly changing using materials that weren't invented 10 years ago. And this sort of disagreement, I had my strong opinions about it. Everybody else had their strong opinions. And at one point, I was reading yet more like arguments about this, and I realized something, that like everybody who talks about this uses the same analogy, which is building a bridge. They say, oh, if we built bridges like software engineers, they would collapse within a second. Or if we built bridges like software engineers, halfway through the client would say, actually, we need a skyscraper. And at some point in sort of being enmeshed in this entire argument, I realized something, which is that I'm using this analogy of building a bridge. The only bridge I ever built was in 4th grade using toothpicks and marshmallows. I have no idea what it's like to actually build a bridge. And then I realized that everybody else in this argument, everybody on both sides saying either like, we don't deserve to call ourselves engineers, or they don't deserve to think that they are even as close to as hard as us. Same thing. They never built bridges either. And that made me realize that if I really wanted to know whether we were engineers or not, I had to talk to actual engineers. And then I realized that wouldn't work either because they had no idea what software's like. The analogy here I use is that imagine somebody says, oh, I know what software's like. I had a degree in CS. I know it is all about proving algorithmic complexity of algorithms and drawing UML diagrams. We would say, you have no idea what you're talking about. So if I really wanted to understand how the two fields like relate to each other, I needed people who have actually worked as both engineers and software developers. And that's what I did. I found these people I call crossovers, people who used to do civil engineering, mechanical engineering, nuclear engineering, and then later became software developers, and asked them about their thoughts.
Exactly. So, and that is the reason why I really wanted to do this episode, because I think it's a very smart way to approach this problem. And also, just a few remarks. I mean, usually this show is in German. So, and in German, we do have engineers, Ingenieure, but software engineers are not really translated to software Ingenieure, but instead are developers, EntwicklerInnen, or programmers, ProgrammiererInnen. And also software engineering is not really translated into something like software Ingenieurswesen, but it's rather software Technik. And software architecture, again, is something completely different. So we don't really have that thing in German, But the reason why I really wanted to invite you is because I was pretty close to writing an article about how we would build bridges, or what would happen if we build bridges the way that we approach software development. So therefore, it's still a very valid point, even though we don't really have that thing in German, and that was the reason to do this episode, my personal reason to do it, because I really want to understand what we can learn from building bridges and whatever else other engineers are doing. So that's the point here. It's not just about linguistics, it's really about learning from other proficiencies, I would say.
Yes.
So what is engineering?
That's a hard question to answer. Before I started this project, I had a pretty good sense of what I thought engineering was. I thought it had to have certain properties. It had to be a licensed profession that was very mathematically rigorous, that dealt with high consequences in real world material. And then the more engineers I talked to, the more I realized that none of those things actually applied. In the end, the only definition of engineering I can come up with is you go around, you find a bunch of people who are engineers, you ask what they do, and that's engineering. That's not very satisfying an answer, but it's the best I can do.
Which I found interesting because, defining things is usually something that I think is good for starting a discussion about it. But it seems that this is really hard. So there are some misconceptions about engineering. So what are those misconceptions?
Right. So I think a lot of these conceptions really relate to how we discuss the differences between software development and engineering. So as mentioned, the way that I sort of thought about engineering starting out is that it's about physical things. It's about high consequence activity. It's about mathematical rigor, and it's about licensure. I think that's like the four qualities that almost everybody I talked to outside of engineering assumed engineering had. And that's like a really good baseline. Like that will describe maybe like 60, 70% of engineering. But the problem is that remaining 30% doesn't really fit neatly into those categories. To give one example, the idea that engineering is building physical things. Well, one of the people I talked to actually worked as what's called a systems integration engineer, where he was basically negotiating the protocols used to communicate between airplanes, flight control things in what are they called? Air traffic controllers in airports, and large antenna arrays like off to the side. And he told me that his work counted under the category of what's called industrial engineering. This is the Handbook of Industrial Engineering, one of the books he recommended I read. And it's dealing with a lot of things like scheduling and like the layout of a place, things that, or like timelines, things that we really don't think of as physical things. In fact, they also have a set of principles I thought were really interesting. They have two principles they say are really critical to industrial engineering. The uniqueness principle says that each project should be regarded as different from previous seemingly similar projects. Similarity is often illusory or misleading. And the people design principle, people have a stake in a problem must feel like they have a role in finding and implementing the solution. Solutions that are imposed on people can be erroneous and self-defeating. And I don't know about you, but that seems a lot like Agile, doesn't it?
Yeah, and also, I mean, the whole thing, we should also mention that you wrote several blog posts about this, and I'm definitely going to link to those. And when I read through the blog post, the person that you just described, what he seems to be doing, seems to me like interface negotiation in some project, and was pretty close to what I would think is also something that is quite common in software engineering and software architecture. And I never knew that such a job even existed.
Has to get done.
Right. So all of these things, like it's physical, it's mathematical, it's high consequence, it's licensed, it's actually not that true, as you said, and there are at least some exceptions from the rule. And one of the things that I found interesting is that software engineering also sometimes is high consequence because we do build software that controls airplanes or nuclear power planes or things like that. And engineers do too. They design those things too, but they also do low consequence stuff like designing this pencil or whatever it is.
Yes.
So that seems to be something that we sort of share, that there is these high consequence things and low consequence things. And after all, we don't do such a bad job concerning the high consequence things too, right? I mean, software fails, but not that often.
I think it's a mixture that software fails, and there are very high profile software failures that did cause loss of life, but there are also very high profile like mechanical failures that did cause loss of life. One of the most interesting examples recently, which we'll touch on something we'll be talking about later in this interview, I assume, is the Max 737 crash, right? And that was attributed to a software bug. The software failed and people died. Except the investigation turned out that wasn't the full story. What happened was that there was a major mechanical fault in the airplanes. The nacelles, the jet turbines, basically caused major aerodynamic profiles that made the plane unsteady at high speeds. And Boeing had a choice of two options. They were saying, okay, we have this major mechanical problem, we can fix it. Or we could just say, we're going to leave in the mechanical problem and write a software patch that does it. And decide that the second thing was cheaper and easier. So they just let the lower quality, like mechanical engineering, just slide by. So yes, there are high consequence failures in software that cause loss of life, but also high profile consequence failures in mechanical engineering that have the same things. And as you mentioned, there's also a lot of very low consequence mechanical engineering. While of course my day job is a software engineer like everybody else, one of my big passions is I'm a juggler. And I recently bought a recorder to help me like record some of my tricks, and it came with this little device that I could use to remotely trigger like the camera on my cell phone. And it never really works quite well. It doesn't connect properly. It like turns off at random points. The light doesn't work properly, but I don't care. It cost me $5. This doesn't matter. The engineering in this doesn't really profoundly affect my life one way or another. It's low consequence.
Yeah, so we have the first comment in the chat by Duderoot, and Duderoot says, I guess that building a bridge is in an incremental way. It's not that easy as building a software in an incremental way. Also, on a bridge we add parts incrementally, but mostly as final components, or don't we?
And this is going to get to something I'm going to have to admit here. And this is sort of one of the limitations I'm going to say about. Like, I think, learn a lot about this, but there's also a lot I didn't learn. And the thing is, I ended up talking to about 17 people about a wide variety of topics, but those 17 people are just a small fraction of the larger engineering population, and I wasn't able to bring up anything. And I bring this up because there's a lot of questions I don't think I can like answer fully confidently about the nature of engineering. And I'm not saying that those questions are unanswerable. They're just things I didn't really necessarily think about. So I would encourage people who think this stuff is interesting to basically do the same kind of thing. That it's very easy to ask people and learn really interesting things from that. But really pulling back to this question, if we don't really incrementally develop a bridge, I don't really know. Like, I can't speak to the people I talk to, but definitely I have worked in buildings that were still under construction when I was working in them, or they were undergoing repairs or modifications. Looking outside, I can actually see that there are some complete buildings that still have scaffolds on them as they make changes to them. So I think incrementally thing does exist in other fields too. It's not just software.
Yeah, and so I think one of the things that you did mention in your blog post is the new Austrian tunneling method, right?
Yes.
And I found that quite interesting.
Right. This was something that one of the mining engineers taught me. So what this engineer did was he used to work on basically making mines safe. In one case, he was tasked with essentially helping figure out how to build a mine under another mine. So there was this large mine that was mining one thing, and they're trying to build a second mine under it to mine a different thing and prevent the ground waste from the first mine from going in and killing everybody. But it might have actually been like a toxic waste dump. It was one of those two things. Basically, the point was to build a second mine under a larger mine. And one of the things he told me is that in mining, there's this idea that came out in the 1950s called the new Austrian tunneling method, which I will admit, as not a mining engineer, I can't really tell you about the full details, but the way he described it, he explicitly said it was essentially agile for tunneling. And this actually does get to something that's really interesting among everybody I talk to, which is this split between agile and waterfall-based development. And what it really boils down to is that nobody likes doing waterfall. Nobody likes having to plan out the entire bridge before it's built. It is entirely a matter of iteration cost. The faster you can iterate, the less you do the upfront planning. So with, say, a bridge where it's really hard to say, build a bridge then modify the bridge, people will like try to design as much as they can out front and build it in one go. But for something like manufacturing a new part or circuit where they could basically design the circuit, then manufacture it, and then see how it works, then basically design a new circuit and manufacture that, people work a lot more iteratively.
So it's a continuum, as you said.
Yeah.
And one thing. So, but surely you don't move bridges, do you?
I've talked to two people who moved bridges after they were built. Two people whose job it was to take a bridge and then move it. There are entire manuals about how to move bridges after they're built. If you Google how to move bridge after built, you will find like official guides by people. If you Google that on YouTube, you will find lots of videos of people at moving bridges after they're built. It's not that common, but it is a thing that has to be done. For example, if traffic patterns change, or if say the like erosion of like a river causes a bridge to no longer be in a stable spot, it's totally a thing that happens. Bridges are moved after they're built.
Yeah, and I think that is probably one of the lessons learned, that you shouldn't assume how different professions go about their profession unless you actually know how they do it. And talking about that, so there was a comment before the show on Mastodon by Carsten Eagle, and he said, I once read, no, so software engineers are not engineers. Engineers work carefully and based on facts, where software developers tend to replace the tail of the plane while the passengers are already boarding. And he said that's from a book by Donis Marshall called Solid Code. And so any comment on that before we continue?
So I looked up Donis Marshall. When you mentioned that to me earlier in like the sort of the pre-show, basically letting people see behind the curtain a bit, we meet about half an hour before the show to sort of talk about things and hash it out. You mentioned that like Bostodon Toot, is it called? Post. And I looked up the author, and he's been entirely in software his entire life. The person who wrote that Solid Code book never worked as an engineer. And yeah, so I think that necessarily is one of those things that I'm trying to sort of work against, this idea that we in software can think about how engineering must work in other fields and therefore just know it, when the only way we can really know is to talk to these people or do it ourselves.
And then he continued. So the Carsten Eagle, the author of the posting on Mastodon, I'm actually not sure about the precise term myself. So he said, further answer, but most software in planes and rockets has no fixed bugs, only documented. Software issues in cars are solved by rebooting the control unit within 10 milliseconds. As I studied both computer science and engineering, I'm not convinced that both disciplines are comparable.
I ultimately can't speak to this person's experience. I don't know if they've worked in both fields, if they've studied both fields like in university, if they're studying on their own. So I can't necessarily say like you have no experience, and I can't say you're wrong. And I didn't ultimately talk to many people about how software works on rockets and planes and cars. So I don't know, it would be very nice if I could sort of say, here's the thing you're missing, but I can't say that right now. I do not have that necessarily background.
But what I thought interesting, because he said that he studied both, what I thought was interesting in the pre-show was that you mentioned that, if someone studies computer science, it's quite different from what you actually do in practice. So therefore, it's probably the same thing for engineering. So if you study engineering, the methods that you are studying might be quite different from what you're actually doing.
That is true. And that does actually remind me of something that one of the people I talked to about the entire, if software and hardware fails, then we just restart within 10 milliseconds. I respond, what's wrong with that as an engineering practice? One of the people I talked to who was a chemical engineer was working on a process for, I believe it was producing rubber at scale. I forget the exact details, but one of the things he told me was that sometimes if the process just fails, or something's wrong, the fastest way to sort of deal with it is just stop the pipeline and start it up again. It'll just fix itself often. So yes, turn it off and on again. That works in every field.
Yeah, have you tried switching it off and on again? Yeah.
Yes.
So we all know IT crowd, I guess. So claim differences. So we already said that engineering is not necessarily waterfall. And we also said that software is, it might not be as unpredictable as we think if we compare it to other engineering. So what are real differences between software engineering and other engineering disciplines?
Yeah, good question. And I've found in sort of doing this research that there are I'd say three major differences. The first major difference is consistency. And that is that software tends to be a lot more consistent than the real world. If I write, say, quicksort, it's probably going to work on two computers of the same type. It'll probably work, depending on how it's written, on two computers with different operating systems, on two computers with different hardware. The virtual world just tends to be a lot more consistent than a physical world. Whereas I usually have like a prop here. But say if we have, say, a battery, I just dropped battery. If I have, say, a battery, it's not really written on here, but if you look at the spec sheets for these things, often the power output can differ by like 10% or the voltage by 10%, or it could be wildly different if it's used in a hot room versus a cold room. Things just tend to be a lot less predictable in the real world. And one of the people I talked to said that what they would do if they say needed a new part was they would send it off to like 3 different suppliers and get back a version of the part from all 3 and then see which one they could most easily modify to do what they wanted. He called it fettling, taking it apart and just tweaking it in little bits to sort of deal with that uncertainty and make it more usable for their purposes.
Okay, what are some other real differences that you're aware of?
Yeah, so the other 2 differences, the other major difference, I'd say, and probably one of the biggest ones, is what I call velocity. And that we talk about as people exist on the essentially waterfall to agile scale, the faster they can iterate, the more you can just do things empirically and just see the results. And software, while similar to engineering in a lot of ways, is way, way, way on the iterative scale. It is incredibly easy to make a change to software and see what happens. By contrast, I think the fastest iteration cycle I saw in any other field was in chemical engineering, where they would have iteration cycles from several hours to overnight. Whereas something with, say, electrical engineering, they'd have to wait for stuff to come back from the foundry, so their iteration cycle might be at 1 to 2 weeks. And that is what allows us to do a lot of our practices that allow us to not necessarily plan things out fully in advance, but very quickly try something, make a change, try something, make a change. A tried and true engineering technique that every field uses when they can afford it.
Yeah, and I think that was also something that you mentioned in your blog, that all the other engineering disciplines are trying to move faster in that regard, and to have shorter iteration cycles, right?
Yes. And most often the way they do this is with software. So things like finite element analysis in mechanical and civil engineering, or like using, what is it called? What are those electric circuit diagram things called? Never mind. But basically software is really, really heavily used to simulate things in the abstract and do this iteration much, much faster in other fields. This is also why for example, the 737 thing happened. It takes a long time to iterate, do one iteration on, say, a mechanical or aerodynamic issue, but it's very fast to do a software iteration. So they said, "Oh, we've got this bug with the mechanical layout. It's faster for us to just fix it in software." Mm-hmm.
Which again might be another point why, or another reason why you want to get up that velocity and why you want to iterate quicker, even if you're just doing software, because it seems that other engineering disciplines are trying to do the same thing. I mean, there are software projects that iterate like once a quarter or so, and you want to move away from that. Would you agree?
I'd say I'd agree, yes. I think I wouldn't say this is something that was due to my interviews, but I think just if we see the trend of software over the past, say, 20 years, Joel Spolsky in his talk about what you should check in any company that you should work for, said that one of the most important things is that do they have nightly builds instead of a quarterly build? And this was in 2006. And now a lot of people can do like hourly builds or minutely builds. The faster you can iterate, just in pretty much any field we see, the better off you tend to be.
Mm-hmm. And I need to look up that blog post, but then I will put in a link to that in the show notes. Yeah. Lastly, there seems to be a difference concerning constraints, if I recall correctly.
Yes. A simple example of that is, say, going back to the battery, if the slot for the battery is basically too small, you can't fit the battery in the controller, right? If a machine is a little bit too big, you can't fit it in through the doorway. If it draws a bit too much power, you can't plug it into a thing. software doesn't have this layer of constraints where you have to like, you must have something. So some software does have this, some like hard time software, like say the controller must reboot in 10 milliseconds, right? But there's very few cases where it's like, oh, if you were 11 milliseconds, then you cannot do this. Whereas that's quite often happens in the real world. One of my favorite stories actually was somebody who designed, who basically studied offshore drilling platforms for gathering oil. And he said he once had to install a set of sensors into a on the floor of one of these like 40-foot tall like oil rigs. And the height of the floor was something like 3 meters or something. The machine was 3.1 meters. So what they had to do was they had to go onto the floor above and saw out a square meter, put the machine in, and then raise that floor of that 1 square meter by like 5 centimeters just to fit the machine in. 15 centimeters, I guess, if I said 3.1 meters. Sorry, I'm trying to convert from like imperial, outdated American measurements we still use for some reason.
Yeah, and I really like that story because it's like technical depth in a building, right? I mean, it's very,
Yeah.
it seems very very comparable, and it's
Mhm.
also a far cry from, well, great engineering and beautiful things.
Yeah.
So
Hey, great engineering is expensive. People want stuff for cheap.
yeah, you could argue that this is great engineering because it's cost efficient, and so
That's true.
yeah. So are we different? So,
I think that's a complicated question. And I would say we are different, but we're not special. And what I mean by that is it is true that like there's certain aspects of software engineering that you don't sort of see in any other field. But that's kind of true of every branch of engineering. There are certain things that civil engineers have to deal with that, say, chemical and electrical and mechanical engineers do not. There are certain things that chemical engineers have to deal with that civil and electrical and software engineers don't. Each field has things that sort of make it different. But it's kind of the same way that like basketball is different from, say, football is different from, say, like archery. They're all different from each other, but they all have certain like principles of sport, right? There's all still sports.
okay, so I mean, if you say that you seem to be saying that every type of engineering is somehow special. So, and
Somehow different, but they
sorry,
still share more in common than they share different separately.
but then we are not different at all, right? Because every type of engineering is special then, and then we are just another type or another school of engineering, so to say.
Well, you can't just sort of ignore the differences. Like you still have to say that, like, okay, so these are different properties of software. It's got different sense of constraint. It's got a different sense of velocity, et cetera, that make the challenges to it very unique compared to other fields. But it still has a lot of challenges and similar. So you have to recognize these similarities, but you also have to recognize the differences.
So would you say that the difference between software engineering and other types of engineering? So I mean, if you compare civil engineering to software engineering, and you compare, I don't know, electrical engineering to civil engineering,
Mhm.
is software engineering so much different from all the other engineering so that it's really, really special and a special breed of engineering, or is it just another special thing and they are all somehow special?
I'd say off the top of my head, it's more the latter. It has its own special things, but every field of engineering is special in its own way. We love all of our children equally.
Okay. So, and that leads to the question, so what can we learn from other engineers? And that is something that you also ask those crossovers that actually have some practical experience in other types of engineering. So what did they say what we should be doing differently?
Mhm. And that's honestly, I think, one of the weakest parts of my work, because I ended up being more interested in what sort of goes the other way, what software is developed that those other engineering fields could use. And it turns out that everybody sort of had similar like thoughts on that direction, whereas what we could learn from other fields ended up being like a bit more like scattered. Everybody had their own small things. And slowly I was able to sort of pierce together across these like 17 interviews or so that um, two major things I think are worth talking about here. The one is basically upfront planning. So we sort of talked about the upfront planning versus iterative like work spectrum. And I say that the way it works is that, like, according to the people I talk to, we're over here, like on the far end, but we think we're over here, like really, really, really off the deep end. And they said that they really wished they had more like time to for planning, not to the level of their old jobs where they were like planning for like days or like weeks or months, but like being able to plan for like hours or days and just being able to sit down and say, okay, here's the system we're building. We might have to change it from iteration, but can we have like a plan to start out? And I honestly like this answer because, again, it kind of ties into what I do professionally. Formal methods is really great at like coming up with these first degree plans. So of course, this is going to be a takeaway I have to give me more money. The second takeaway I think is way more interesting, which is that these other fields have a lot more material on what I'll call domain topics. Like in software, we have like a lot of books on, say, how to use Kubernetes or like how to use Java, etc. But there's not that many books on, say, how to build a user profile or like how to manage a plugin system or how to or required features of a social network. But these are things that we've been doing for long enough that we have good senses of what either does and doesn't work or different ways that could work that have trade-offs, right? Like we know, for example, if you're building like a user profile, like a social network system, you have to have some ability for people to mute others and block others. Otherwise, your system is going to be taken over by bad actors and cause harassment and stuff. And this idea of sort of in a domain, collecting the knowledge we have and trying to put it in one place that people can learn very quickly is very common in other fields. One book that one person recommended to me was called the SnapFit Handbook. A SnapFit is this thing. So basically, if I take this and I open it up, it sort of fits in with this little hook. You see that there? It snaps in and it fits. That's called the SnapFit. There's an entire like 400-page book on various trade-offs in making SnapFits. For most topics in engineering that have been done long enough, there's a book somewhere that talks about everything that was done up to that point, some of the pros and cons of each. I think that's the thing that software can be a lot better at.
Okay, so I really want to dive deeper into these things. So concerning the methodological process, I mean, there are things like no big design up front and you ain't gonna need it. I think they originate from the extreme programming movement from last century. So are you saying that they were wrong, or what's the point here? And this is still something that is around. So actually, I did an episode about architecture mistakes last week, and one of the persons there said that he was guilty and still is that he was guilty of not conforming to you ain't gonna need it, and that he found that this was a mistake that he made. So how does that fit together with this idea of more planning ahead?
So I believe that you ain't gonna need it comes from the early 90s with the rise of extreme programming, right? And the principle of you ain't gonna need it, if I recall correctly, I haven't looked it up recently, is that you should be you shouldn't basically put in features that you think you'll need but don't know you'll need, right? They think, oh yeah, we'll probably need this functionality. We should add it in advance even before the customer wants it. And I think that is often a good principle. It prevents people from sort of like going too far off like the deep end of just trying to build stuff that they think would be cool but aren't actually necessary. But the difference is that that's really good if you don't know you're going to need something, right? But I think now we have enough experience in enough fields that for certain domains, we can say, no, we've seen time and time again, you will need this very quickly. You will always need your work queues to have a retry mechanism with exponential backoff. You will always want some way to like log requests. You will always want some way to block somebody else in the social network. Because as soon as these things are built, people add them.
Okay, so basically that's what you said before, that we are too radical concerning you ain't gonna need it, but there's still some truth to it. What about big design up front? I mean, that seems to be what you're suggesting, right? To sit down before at the beginning of the project and to make up your mind about what you want to do, and this really sounds like big design up front, doesn't it?
Yeah, I'd say the difference is design up front versus big design up front, right? Like, big design up front was sort of like a reaction by, I believe, either the extreme programmers or the agile against the way of specifying everything in advance, like going forward, right? And I'm not going to sort of get into like the arguments about like what waterfall really was. I've written about it when I was on this conference previously. I was with Laurent Bosavi, right? He's written a great deal about what waterfall originally was in his excellent book Leprechauns of Software Engineering. But generally, the idea is that like at least as we think of it, as big design upfront is you design everything, you create your rational unified process, you have figured out all of your classes in advance, you figure out all the relationships with the classes in advance, then you start writing. What I tend to do in my work is much more what I call specifying the abstract machine, where I'd say if I'm like making like say a 10,000 line program, I might write a 300 line specification and then sort of see the abstract behavior of that specification, verify that works before designing out the program. So it's still design up front, but it's not like designing everything. It's designing the most important part that you probably might not necessarily need to iterate on to change that. And then if we do need to iterate, we can change the abstract design because it's a lot smaller and more focused. See that works and then work on that.
And at the end of the day, I mean, when I read through your blog post, it seemed to me like this is just important feedback from the outside. I mean, other disciplines that basically said, okay, you might have gone too far in that one direction, and that we should consider moving a little bit backwards. So I think that's a good point.
Or to be more precise, the people who used to be in software engineering, other forms of engineering that became software engineers, wish they had that from their old field.
Right, which means that there might be some value to it because they do have experiences and that might be a lesson learned. The other thing concerning the predefined components, so reuse was the big hype in the 90s, right? When everybody was thinking that we build those reusable components and we will have much better productivity because we're just going to reuse that code. That never really worked out. So why do you think that this could somehow be different now, or how should we do it differently now to make it actually work?
So disregarding whether or not it worked out, I think that you could argue that, for example, one of the stunning successes of, say, the NPM and Node World was that they made components really reusable. But let's disregard all that discussion right now to focus on I think the main difference between what I'm saying and that like failed goal is that I'm not saying that we should make plug and play solutions. I'm saying that we should be creating the knowledge that goes in the mind of the programmer. Like maybe making a reusable, I don't know, user profile like module will not work. But I think what definitely will work is like if you're making a user in your system, here's the things you need to think about. Here's the common pitfalls that happen and the problems that are caused by following these anti-patterns. That's, I'd say, the fundamental difference, the idea of a pattern versus a library or a reusable solution.
So we are basically what you're suggesting is some kind of pattern language or set of pattern or collection of patterns that actually talk about
not even a language, just like essays, books, knowledge, information.
That basically so like a book that says, okay, this is how you would usually build a user profile. This is how you usually deal with subscriptions and so on, and then do that. Yeah. So
do you mind if I just quickly walk around and grab an example of this from my library?
Yeah, sure.
I'll be back in 1 minute if I do this. One second. I think this book is a good example. This Documenting Software Architectures. It's even a bit more broad than I'm talking, but it has some of the same ideas. One of the chapters in it is let me see if I can find this really quickly. Is basically on different ways of having connections between systems, like the topologies. So if I've got the right selection, it talks about I haven't pulled this out in a while. Component connectors, right? So it talks about a set of different topologies of basically distributed systems. So the topologies that it talks about are pipe and filter, shared data, where basically everything is working off a single shared database, pub subsystems, client server, and peer-to-peer. And for each of these, it talks about here is what this architecture roughly looks like. Here are some of the advantages of this architecture. Here are some of the weak points of this architecture. Here's where it doesn't really do a good job. And here's like our opinions on like when it should be used. And you can basically disregard its opinions on when it's to be used. You might say, actually, you're wrong about when it's best. But the description of what it looks like, the advantages it uses, and like the drawbacks, I think are very, very like valuable. Being able to say, okay, so one of the problems of shared data is it causes major like security and privacy issues because you can't really scope things as well. I think that's valuable information that you might not necessarily know unless you've either built the system yourself and run into these problems yourself, talk to somebody who's done this, or read a book like this, documenting software architectures.
Okay. Yeah, I'll put a note in the show notes, and that's interesting because that seems to me like a technical decision, while things like user profiles or subscriptions are rather something that I would consider domain logic. So what you're saying in a way is that also with these more technical things, we could profit from these more abstract descriptions that talk about how you would actually solve these problems.
Yeah.
I think. Okay. So as you said, you're really interested in, and in your blog post, you also mentioned professionalism. So is that something that we should talk about, or is that just something that we leave to the blog post?
Let's leave it at the blog post. It was something that like a lot of people, like a couple of different people brought up. They felt that their older work was more professional, but it was more like a vibe they had than like a very specific things they could give me as like discussion. So I think talking about that would end up being like a bit twisty and like fold on itself, which is why I think it's better to leave to the blog post.
Yeah. Okay, cool. So what can they learn from us the other way
Now,
around?
this was really exciting because I sort of got like a bit of piecemeal information from like every different person I talked to about what we as software engineers can learn from other fields of engineering. But what they can learn from us, everybody basically gave the same two answers. The first answer is what's called openness. And this really ties into one of the questions I think a lot of people have, which is if software engineering is like other fields, why are there so many software engineers and so few of the other fields? And there's a lot of reasons for this. But I think one of the really big reasons nobody talks about is that it is so much easier to self-teach yourself software engineering than any other field. Like if you want to become an electrical engineer, at the very least, you need an oscilloscope. For a chemical engineer, you need a lab to work with. But everything a software engineer uses is on the computer. And not just that, but we are incredibly good at sharing information. No other field has something like GitHub, where you can just look at 200 million public code bases for completely free. Other fields don't really have the same level of just free blog posts that like we do, where just I will have a blog with hundreds of thousands of words on topics of software engineering just for free. And what shocked me most is that, so this is let's just put it, this is the JAX t-shirt for JAXConf, right? And JAXConf, would you say, is a conference where a bunch of software engineers talk to each other about being better software engineers. Is that something you would say about JAXConf?
Yeah, definitely.
That does not exist in other fields of engineering. Every other field of engineering has two kinds of conferences. Academic conferences where like researchers get together and talk about their research, and trade shows where a bunch of manufacturers get together and try to pitch their services to like other companies. The idea of just having a conference where engineers come together to become better engineers with each other is unique to software.
And I thought that was quite interesting because, I mean, it is something that I think is quite valuable in our community and
incredibly valuable.
And actually, what we are just doing is one of the examples of this. And also, there are the conferences, as you said, your blog, and lots of stuff. And it's just that it's hard for me to imagine what our community and our industry would look like if we didn't have that. So.
One of the most shocking like things that happened was with a German chemical engineer. I was talking with her and she asked me a question at the end, which is like, in software, I've talked to so many other software engineers. In my old job as a chemical engineer, the only other chemical engineers I talked to were my coworkers. What do other chemical engineers say chemical engineering is like? I want to know. And it just shocked me.
Yeah, that's definitely. Mm-hmm. I mean, you wonder how they even can improve their profession that way.
Yeah.
Okay, and what else is it that they thought was valuable and could be taken
Yeah.
away from us?
So it turns out like openness and having this free levels of communication is the minor thing people wanted. The big thing that every single person mentioned, gay. Other fields have version control, like some form of it is called change management. And like there'll be some software that lets you sort of keep old versions of like your change. Nobody has anything close to the power of version control in software. The ability to sort of say, hey, there was this test that failed. Find me the exact commit who added that test, which line added that test, who added it, does not exist in any other field. Nothing close to it.
And even in fields that could do it. I mean, I've published a few books, and you give them the manuscript, and they put it in the layout, and then there is no way to reconstruct the layout from the manuscript, but instead you have to have some manual process where you say at that line you have to replace that word, and so even in publishing it, version control and having the ability to easily change something is not a given.
I mean, everybody's seen final.docx, final1.docx, final1 underscore actual final.docx. Like version control is something that pretty much every field would incredibly benefit from. And this does not exist outside of software engineering at the degree we have it.
Yeah, and what you just said concerning Word documents and version control in with file names is a good example. So there are a few questions in the chat. So Dudrut asked, would modeling a software at the level of the second level containers modules in C4 and the C4 model of software architecture documentation considered as big upfront design? Isn't doing everybody at least this when they start a new project? So this seems to be like a rough cut about, okay, this is what we're going to build. These are the, whatever you want to call them, components and how they will interact with one another. So would that already be considered big design up front?
I think that people who use big design up front as a like insult would say it might be big design up front. I, as a person who likes doing upfront design, would say it's not big design. It's in the good zone of like totally fine. I will admit I've never tried using C4 like myself on a project, but it seems interesting and it seems like the kind of thing that would be a useful tool for people.
Yeah, and I think if you talk about big design up front, I think you have to take into account what the world was like in the 90s when there were like literally hundreds and thousands of pages of documentation before you even started the project. And I think that is what people were tired of. So, and that is what really was too far on the planning side of things.
One of the things I did notice, at least when talking to some of the civil engineers, is that there's usually multiple layers of blueprint. There's like a layer where it's just like very, very high level, very abstract. Then like for each one, you can create a progressively more detailed refinement. And I think like there is some point where it turns from being like big design, regular design to big design at some level of refinement. And we could still do the high level abstract stuff without having to be incredibly detailed, trying to write out every class in advance, figure out every module in advance.
Yeah, and also, I mean, that is why the impression that I got from this new Austrian tunneling method is that you don't really plan that much ahead in that case, and you're sort of bound to react to what happens. So it probably also depends on what you're building, right? Whether you're doing.
I mean, I'm afraid I do not know details about the Austrian tunneling method. So it was brought up as an interesting example of like agile in other fields, but I didn't spend the time. I didn't like spend that much time like learning it myself because I wouldn't understand it. I'm not a tunneling expert.
Yeah, and there you go again, right? I mean, that's the whole problem that if you don't really did it yourself, then it's hard to see what it's really like.
Yeah.
But it's interesting to notice that there are different types of blueprints, and I think that's quite quite a good point. The next question or point about you from Root again is also in construction, more engineers start. I'm not sure. Let me just read it for myself because I'm not sure what this actually means.
Do you want to post it into the Zoom chat so I can sort of read it too?
So it says also in construction, more engineers start creating content about what one should do or not do when building a house, for instance. Not sure.
Yeah.
Oh, so that was probably referring to what you said, these predefined components, and to talk about what these user profile subscriptions and so on, that there is more content for house building, which is in a way quite interesting, by the way, because what you said is that there is more openness. But then again, there seems to be more content about specific things in the other engineering disciplines. So I found that that's quite interesting.
Yeah, I guess there's a lot more houses than any other kind of building, right?
Yeah, maybe. And therefore, but maybe it's also about us being so very interested in technology. I mean, Kubernetes is cool, but user profiles are not, and maybe that's another point there.
Maybe, and I think it's also just that it's easier to talk about like a technology than to talk about the mix of a technology and a problem domain, because problem domains get way messier.
Exactly, and even though they are the ones that really matter, because at the end of the day, it's about solving the problem. Okay, I think we are. Anything else you want to add? Anything that you want to say?
Yeah, so I guess I want to say two things. One is that people are incredibly open to being talked to. Like when I got like these names and like people reached out when I was doing the search, most people were just like, yeah, fine, I'll talk. I'll do an hour interview. So, and this happens with most of my journalism projects. It's very, very easy to get somebody to just talk about their experience in their field. So if there's a question you want to know, they think could be answered by another person, just feel free to reach out to them. You'll be surprised at how many people are happy to help you. And second is that I think I learned a lot, not just from this being about the crossover between engineers and software developers, but about the crossover between any other field in software. I think there's a lot that we can learn from every field. And I think that there's a lot every field can learn from every other field. So, I mean, if you are a person who, say, switched from being a chef to a software, or a social worker to software, or a journalist to software, and you like write about your experiences, write about how they're similar and different, that would be something very valuable to contribute to our overall knowledge of software engineering. I would like to see that.
Yeah, that's a good point. And you just reminded me about 2 episodes that I did in German, I'm afraid. So there is one that I did with some pilots about crew resource management, because I thought that was quite interesting about how they organize and how they make sure that they communicate openly with one another, and how important it is to communicate openly with one another in an environment like airplanes, and that there are airplane crashes that are basically about communication and also cultural failures. So maybe that is something, if you're a pilot and you're now doing software engineering, maybe that is something that you want to elaborate on. And I also did an episode about Auftragstaktik. I'm not sure how you would translate that to English. It's a military style, so it's a style where you would give them some kind of objective and explain them why you want to reach that objective. But it's not like command and control where you would tell them to do exactly that, but instead you say, please reach that goal. It's somehow comparable, I think, to management by objectives. And I found that, again, interesting, because it seems that this delegation of power to other people and to let them figure out how to do it, and leave them to their own devices to solve the problem. This is something that military actually also does, and maybe that is also something, if you used to be in the military, and you're now doing software engineering. So
there's actually two other, if you've got the time, 2 other things for the military I think are really fascinating in their application to software. One is the idea of a war game, right? which is basically just getting a bunch of commanders to like simulate out a battle or like a military campaign and talking about what worked and what didn't. I think we're starting to see the same ideas appear in, say, like DevOps with trying to simulate like failures, or in security with simulating like intrusions. I think that's like a really interesting idea that comes out of military. And the other one that I've recently fallen in love with is the concept of military friction, which is all the things that happen on a campaign that basically make you miss objectives and like cause things to fail and cause things to like collapse, like bad weather, or like key personnel getting sick, or like dying, or just reading the map a little bit wrong. And I think this concept of friction really applies to almost every field of like trying to execute a really complicated strategy or plan. So yeah, definitely a lot of stuff to learn from military.
Yeah. So so there are lots of interesting things. Yeah. So I think we sort of wrapped it up. So thanks again for joining. Thanks again for listening, and for all the comments and questions. And so next week we will be doing a broadcast of 2 talks in German, I'm afraid, on
I mean, not for the audience. For me, it's You're Afraid.
for on Tuesday evening. And I'm not sure whether we're gonna do whether I'm gonna do a show on Friday. We'll see about that. Okay, thanks a lot, and have have a great rest of the week, and thank you for being on the show.
Thank you for having me, and have a great evening.